looking at the graph of a reciprocal quadratic function. So reciprocal quadratic function is when you have 1 divided by some quadratic function. So this general form, ax squared plus bx plus c, could apply to absolutely any quadratic at all. Now, when you studied quadratic functions, you've learned that a quadratic function may have no roots, 1 root, or 2 roots. So let's say f of x is 1 over ax squared plus bx plus c. You might have a situation with no roots, and that's to the denominator. And you know what we call that when it's the reciprocal of a quadratic? Well, any rational function. We call the root of the denominator a pole. So you may have no poles. That comes out of control theory, if you want to look that up. Poles of transfer functions are related to the stability of a system that you're controlling using feedback control. So a function like this may have no poles, which really just means that the quadratic at the bottom has no roots. Or it may have 1 pole, which means there's 1 double root to the quadratic. Or it may have 2 poles. And the poles turn into vertical asymptotes. So if you have no pole, then your function is going to look like this. If you have 1 pole, your function, let's say the pole is right here, your function is going to look like that. And if you have 2 poles, then you're going to have 2 asymptotes, and your function is going to look like this outside of the asymptotes, and it's going to look like this inside of them. So whenever we have the reciprocal of a quadratic, if we have no poles, that is no zeros to that quadratic, meaning there's no solution to making that quadratic equal to 0, it's going to look like this one here. If you have 1 solution to your quadratic, there's going to be 1 asymptote. That's like the double root situation. It's going to look like this. And if you have 2 distinct roots to the quadratic, then the reciprocal function has 2 poles. The roots give you the location of the vertical asymptotes. And if you have 2 poles, that is 2 roots to the quadratic, then it's going to look like this. And I'm going to show you how to deal with each of those cases now. So let's start out with, we'll start out with the 1 pole case, because that's the easiest one to deal with. So consider this function, f of x is equal to 1 over x squared minus 4x plus 4. This quadratic, your easily factors your 2 numbers that multiply to give you positive 4 and add up to give you negative 4 are x minus 2 and x minus 2. So this is 1 over x minus 2 squared. That gives us a vertical asymptote at x equals 2 because we have a pole at x equals 2. So when I go to plot it out, I can go over to x equals 2, and that's the location of my vertical asymptote. As x approaches 2 from the left or the right, this approaches infinity. So as x gets closer to 2, we get closer and closer to dividing by 0. Let's say we're approaching 2 from the left. So we've got a number like 1.9. F at 1.9 is going to be 1 divided by 1.9 minus 2, and that's being squared. So that's going to be negative 0.1 squared, which is 0.01, so this whole thing is going to be equal to 100. I'll let you plug that in, verify that for yourself. As x approaches 2 from the right, you're going to see the same thing. If you put in a value like f at 2.1 or f at 2.01, you're also going to see these large numbers come out, and they're all going to be positive. So that tells you that as x approaches 2 from either side, y approaches infinity. So that's how this behaves around the asymptotes. It's as you approach it, it makes its way up. So as we approach from the right or the left, that function goes up. As for your horizontal asymptotes, as x approaches infinity, you're dividing by a larger and larger number, y is going to approach 0. And because everything's being squared, this is always positive, so it's approaching 0 from above. Likewise, as x approaches negative infinity, y is approaching 0 from above. If you've not yet done calculus, that's why you're watching this. You don't quite know what a limit is, don't worry about that. For now, just put in larger and larger values for x, and you're going to see that it gets closer to 0. But that plus means it's always above 0. It's never below 0. It's always a positive number going towards 0. So with that end behavior, as x goes to infinity, y approaches 0. And as x goes to negative infinity, y approaches 0. So it's going to look like that. I'll plot it out here. We've got y equals 1 divided by x squared minus 4x plus 4. So that's the graph that we originally are looking at. 1 over x squared minus 4x plus 4. And as you can see, there's a vertical asymptote where x is equal to 2. And as x approaches infinity, and as x approaches negative infinity, this thing approaches 0. So that is our first case here. Sorry, that's our second case here. It is the one pole case. You have one pole when there's one x value that makes the entire thing equal to 0. I'm now going to show you the two pole case. So consider we've got f at x is equal to 1 divided by two x squared plus x minus 6. What we want to do right now is factor the bottom, and if you're not quite sure how to do that, I've got videos on how to factor, so I'm not going to show you how to factor now. Let's just assume that we can. We'll factor this, and we get f at x is equal to 1 divided by 2x minus 3 multiplied by x plus 2. Okay, now there are two x values that will make the denominator equal to 0. That gives us two distinct poles. Our denominator is 0 if 2x minus 3 is 0, or if x plus 2 is 0. So these are our vertical asymptotes, our VAs. We have vertical asymptotes at the poles. The poles are the x values that make the denominator equal to 0. So in one case, we've got 2x is equal to 3, or x is equal to 3 over 2. Sorry, those 3's are ugly. 3. And then in the other case, we've got x equals negative 2. So I've got two poles. One is at 3 over 2, and the other is at x equals negative 2. So I've got two poles, one at negative 2, and one at, so I've got one vertical asymptote here at x equals negative 2, and the other one is at x equals 3 over 2. Well, 1 is 2 over 2, and 2 is 4 over 2, so 3 over 2 is the halfway point here. It's 1.5. So that's my other vertical asymptote. So again, the x values of the vertical asymptotes, 3 over 2 and negative 2, are the zeros of the denominator, 3 over 2 and negative 2. Now, as x goes towards infinity and as x goes towards negative infinity, I'll let you plug in values for yourself. You're going to see that this goes to 0. And not only does it go to 0, but it goes to 0 from above. So the bigger the value you put in for x, either positive or negative, you're going to get a positive number above 0, but that's approaching 0. So you can plug in f at 1,000,000, f at negative 1,000,000, and verify those for yourself. As x approaches infinity, y approaches 0 from above. So this way and this way. How about as x approaches the asymptote? As x approaches 3 over 2 from the right, if you plug in values just slightly bigger than 3 over 2, you're going to see this. And as you plug in values slightly less than negative 2, so as we approach negative 2 from the left, you're also going to see that it goes towards positive infinity. So here, this is our asymptotic behavior. And again, we've got f at x is 1 over x squared minus 2x squared plus x minus 6. And as x approaches 3 over 2 from the right, and as x approaches negative 2 from the left, in both of those cases, y approaches infinity. So again, to verify this, for this one, put in values for x slightly bigger than 1.5. So look at maybe f at 1.51 or f at 1.501. So that's values approaching 3 over 2 from the right. To figure out what's going on as x approaches negative 2 from the left, put in values just below negative 2. So put in values like f at negative 2.1 and see what's happening to y. So you plug those values in, you're going to see large y values, and those large y values are going to be positive. Now for the trickiest part of this. What's going on in between the two asymptotes? So in between the two asymptotes, this cannot cross the x-axis. It stays entirely one side or the other side of the x-axis. It kind of resembles a parabola, except a parabola is defined anywhere for x, whereas this is only going to be defined between the two asymptotes. So it's going to approach infinity or negative infinity as we get arbitrarily close to those asymptotes. Also, it's going to have a local max or minimum value. Now, I'll just quickly sketch what this is going to look like and then show you in detail how to figure out exactly what it looks like. So broadly sketching this, remember we had vertical asymptotes at -2 and positive 1.5. That was positive 3/2. I'll write it in as 1.5. And our graph looked like this on the outside of the asymptotes. And we're trying to figure out what's going on the inside. What this is going to look like in here is as we approach 1.5 from the left, so as x goes to 1.5 from below it, like 1.4 and so on, y is going to approach negative infinity. You can plug in values to verify that for yourself. So as we get closer to here, it's going to approach negative infinity. And as x approaches -2 from the right, so with values like -1.9, -1.99, and so on, it's also going to approach negative infinity. Somewhere in between the two, we're going to get a local maximum value. Now, what is this local maximum value going to look like? Well, we have symmetry in this situation because we're dividing by a quadratic. So what we do know ahead of time is that that local maximum value is going to occur right at the halfway point between the two poles. So all I've got to do is find the halfway point between -2 and positive 1.5. That's going to give me the x location of that local maximum. I can then plug that x location into my function to determine the actual value that I have here. So my local maximum, that is, when I've plotted this, I've got right here, that's my local maximum. It's going to happen at the halfway point between the poles. So the local maximum is going to have an x value that is the halfway point between -2 and positive 1.5. So I'm going to average those two out. So the x location of my local maximum is going to be 1.5 minus 2, which is -1/2 divided by 2, -1/4. -0.25. That's the x value of my local maximum. So what is the y value of my local maximum? I'm going to take my function and evaluate it at -0.25. So I've got 1 divided by 2 times -0.25 squared plus -0.25 minus 6. So I can use my calculator, figure out the value here. So I've got 1/4 squared is a 16th. That's 2/16 minus 0.25 and minus 6. That's going to give me 1/-6.125. So my actual value is going to be negative 0.16. That makes the y value of that top part negative 0.16. So let's put all of this together. We've got vertical asymptotes at negative 2 and positive 1.5. We've got a local maximum with a value of 0.16. And our end behavior is as x approaches infinity, y approaches 0 from above. As x approaches negative infinity, y approaches 0 also from above. And with that being our local maximum, as x approaches negative 2, y approaches negative infinity. And as x approaches 1/2, y approaches negative infinity. So this is the two-pole case. Remember, we found the location of that maximum by taking the x value as the average between the two poles and then plugging it into f at x to find the y value. So this height here, the value of this height, you can get by, it is f at the average between the two poles. Two poles being the zeros in the denominator. Take the average of those two numbers, evaluate f, that's going to give you the height. Okay, now let's look at the no pole case. So let's say I've got f, let me switch that back here. Let's say I've got f at x is equal to 2x squared. Oh, we're doing reciprocal, so it's 1 over that. F at x is 1 over 2x squared plus 4x plus 3. Now we're looking for vertical asymptotes, so we're trying to determine when our denominator is equal to 0. So you try and solve something like 2x squared plus 4x plus 3 is equal to 0. We're doing this to find our poles. And remember, our poles are the location of our vertical asymptote. However, when you go to do this, you'll notice that if this is A and this is B and this is C, in the quadratic formula you try and take the square root of b squared minus 4ac. We call that the discriminant. And notice that b squared minus 4ac in this case is equal to 4 squared minus 4 times 2 times 3. 4 squared is 16. 4 times 2 times 3 is 24. And this gives us negative 8. Because b squared minus 4ac is a negative, we know right away that this has no roots. We're not even going to bother trying to factor it. This has no real roots. And because this has no real roots, there are no poles, there's no vertical asymptote. So what this is going to look like is a speed bump. With no asymptote, when we plot this out, it's going to look like this. The only question is, what is the location of the speed bump? Well, the location of the speed bump is going to match the vertex of the quadratic at the bottom of our reciprocal function. So f at x is, let me remind you, it's 1 over 2x squared plus 4x plus 3. this thing we have on the bottom is a quadratic. Every quadratic has a vertex. We're going to find the location of this vertex. That's going to be the location of our speed bump. Now I know you've learned to do this by completing the square, but there's actually a little trick that I'm going to show you here. So we want to find the vertex of that. So let's remind ourselves we're going to find the vertex of 2x squared plus 4x plus 3. So we know this is a quadratic that has no roots. We want to know what its vertex is. So it's something that looks maybe like this, and we would like to know the location of the vertex. What I'm going to observe is that this quadratic is the same thing as 2x squared. It's the same as 2x squared plus 4x, except we're adding 3 to it, which would shift it up by 3 units. You know what that tells us? That tells us that it's going to have the same vertex, x value, as 2x squared plus 4x. It's just shifted up. So 2x squared plus 4x, I'll graph it below, it is that. These two are going to have the same vertex. They line up perfectly. It's just this one is the same as that one, only it's been shifted down. What's the vertex of this going to be? You can pull x out, 2x out as a common factor, and you end up with 2x times x plus 2. Because 2 times x is 2x squared, and 2 times x times 2 is 4x. This parabola has roots at 0 or -2. So what that tells us is we have a root here at 0, we have another root here at -2, and this parabola here has exactly the same vertex x-coordinate as this parabola here. See, this top parabola is this one, and the bottom parabola is that one. By shifting it down 3, I've guaranteed that I have roots, and I have roots that are very easy to find because with no constant term, we can just pull out a common factor to find them. So all we need now is the x location of the halfway point between 0 and -2. What's that going to be? Well, it's the average between 0 and -2. It's -1. So our vertex is at -1, and then we just need the y value. Well, the y value at -1 is just your function at -1. So it is 1 divided by 2x squared, so 2 times -1 squared, plus 4x, so that is 4 times -1 plus 3. So that's 1 over 2 minus 4 plus 3, which is 1 over 1, so that whole thing is equal to 1. That tells us that our vertex, that bump, is at -1, 1. So when I go to plot this out, when x is -1, y is equal to 1. As x approaches -infinity, y approaches 0. And as x approaches infinity, y approaches 0. It's going to look like that. This is the no pole case. And in the case of no poles, you're going to find the location of the speed bump by taking the average of the two roots. Now, of course, there are no roots because there are no poles. So the trick that we've employed here is instead of trying to find the roots of this, you copy it out, except you ignore the constant. We scratch that 3 out, guaranteeing that there would be 2 roots of this shifted down function, and the average between those roots is the location of the x-coordinate of our vertex.